Hello, everybody, and welcome to Orchestra Hall for this week's Chautauqua Lecture Series. I am not John Mann. I am Sarah Twitchell, and this summer I'm going to be filling in for John when he gets double booked for things. And so he asked me to come today and introduce our speaker. This year we're celebrating cultural and geographic regions in the United States, and for this week of the lecture series, week 2, we're exploring the 49th and 50th states. We're fortunate to welcome Dr. Jason Briner here today. He is a professor of earth sciences at the University of Buffalo, where he teaches courses on climate change, geomorphology, and advanced courses on glaciers and paleoclimate. Jason's presentation, Waking Up from the Last Ice Age, will highlight the ongoing University of Buffalo research program using geological and biological techniques to reconstruct past changes involving volcanoes, glaciers, and ecosystem shifts and changes. We hope you can come back later today when Jason will give another presentation for the Environmental Lecture Series. That session that will be here in Orchestra Hall at 3:30 is entitled, Why Greenland Matters. Please be sure to turn off your ringers on your cell phones and help me in welcoming Dr. Jason Briner.
Thanks very much. Perfect. Okay, now, the mic is on. That's good. Well, anyway, thanks for joining me this morning for this lecture about Alaska. Raise your hand if you've been to Alaska. Wow, most of you have. What about Southeast Alaska, or what's called the Panhandle in Alaska? Anybody been down there? All right, so that's where I'm going to talk about today, Southeast Alaska. The title of my talk is Waking Up from the Last Ice Age. So I'll have themes in this talk today that span from the Ice Age and how we transitioned from the Ice Age that our planet was in not long ago, geologically speaking, and how we woke up and we come into today's world. So this talk, just to let you know up front, it describes an ongoing research program that I operate at the University of Buffalo, where I'm a professor, where we're reconstructing changes in glaciers and ice sheets, and also sea level in Southeast Alaska. So to start, if you could get one word to use to describe Alaska, what would that word be? Huge. Huge. Diverse, beautiful. Cold. Rainy. You've been to Southeast Alaska, I can tell. Yeah. No bears or eagles or whales or Denali. That's where North America's highest mountain is. You can see Russia from. You can. Russia's not too far away. A lot of people see or visit Alaska. You know, they go to Denali National Park, kind of in the middle of the state. This pointer may or may not work, so I probably won't use it. You know, a lot of people go to Denali National Park, which is in the middle of the main part of Alaska. And then a lot of people visit southern Alaska and southeast Alaska via cruise ship or the Alaska State Ferry System. So that's what these maps show, is the routes of the ships that you can take to visit a lot of really cool towns in southern and southeastern Alaska. Sometimes you can even leave from Seattle and go through British Columbia and then go what's called the Inside Passage in southeast Alaska. That's shown on this map on the right. Okay, so I'm going to talk about research in southeast Alaska mainly, and I want to tell you about why we do our research down there. Before I get into the science, I just want to share with you some of the scenery about why many of you have been to Alaska and why a lot of people like to go to Alaska. Just going on the Alaska State Ferry System, it's like taking the bus from here to Toledo or something. You just take the ferry from one town to another town and you see wildlife and glaciers and mountains. There are puffins in Alaska, and of course people go to fish as well. In terms of me, so just to let you know, we said it already, but I'm at the University of Buffalo, which is on the other side of Lake Erie. It's the part of the lake that gets all the snow. So the water out here goes in the atmosphere and goes to Buffalo, and that's where we get it all winter long. It's just, if you had a boat, you could just go right here and go zip, and next stop would be Buffalo up there. So that's where I am today, but I want to let you know real quick where I started. And where my journey started as a glacier scientist, broadly I'd say that's what I call myself, was when I was in college. I was a student in Seattle, Washington, and I went to the local university, the University of Washington. And in 1994, as a college student, just discovered geology as something that I was maybe interested in. I didn't know what my major was going to be. Actually, I started as a mechanical engineer. Then I took a geology class, and I was like, wow, I like this a lot. And I got to take more geology classes, and then because the University of Washington is what's called a research university, professors there do research projects, there was a PhD student named Rob who needed a field assistant because he was going to do some research in Southeast Alaska. So I volunteered for that position, and I got it, and it was just Rob and I kayaking around Southeast Alaska so he could take samples of dirt to figure out when those glaciers were bigger in the past and when they were smaller in the past. So I liked that a lot, and that's when I fell in love with glaciers. And when my eyes were opened with the realization that one could do something like that for a living. You could do research to figure out, using geology and geological techniques, like picking up traces of evidence left on the landscape, to piece together how a glacier that you're looking at today was bigger in the past and how big it was in the past and when it was bigger in the past. And that's what I've been doing ever since. If we forward the clock 30 years later, is that right? Here we are in Southeast Alaska, a crew of students and me collecting samples. The samples we're collecting here is from the bottom of a lake that I'm going to tell you about a little bit later. And I'm going to tell you about how we sample mud samples from the bottom of the lake can tell us about how glaciers have changed in the past. So, what's up? Why do we do research in Southeast Alaska? I was, since 1994, in my first visit, I went away and I did other things, and I did my graduate school work in other parts of Alaska, and then I did my graduate school work in Arctic Canada, and I've done research, which I'll talk about later this afternoon, on Greenland. And in 2015, I went back to Southeast Alaska because there were some interesting research questions that I wanted to bring my research program there to see if we could address. So let's go way back in time to the Ice Age. So in this animation, there are these numbers on top. And the Ka is technical terms for thousands of years ago. That's like a geologic unit for time, K being 1,000, A being year. And you can see the world was in an ice age 20,000 years ago. So that's why the animation starts at 25, goes through 20, and then goes forward to here we are coming up on 10,000 right there, 9, 8, 7, 6. By 6,000, the ice sheets that covered North America were basically gone. That was the official end of the Ice Age. So this is the world transitioning from Ice Age conditions to non-Ice Age conditions in this maybe 10 to 15,000 year time period. You can see there were ice sheets over Norway on the right side, and Russia and Scandinavia. You can see Iceland and Greenland in the middle. And then over here, twisted a little bit because of the map projection, is North America. And you can see a big ice sheet over North America. Anyone know what that one was called? It's the same ice sheet that would have covered this auditorium. Yeah, the Wisconsin is the time period. Wisconsin, but it's colloquially called the Wisconsin ice sheet or Wisconsin ice sheet. And we call it the Laurentide ice sheet in technical jargon. That Laurentide ice sheet covered Lake Erie. It flowed all the way down to Cincinnati. Does anyone know of any evidence locally that is evidence that that ice was here? This is the world famous glacial grooves. This is world famous. When people think about the geological wonders of North America, they think about the San Andreas Fault in California and Yellowstone and they think about the glacial grooves preserved on Kelly's Island. Last summer, here's my two boys, last summer on Kelly's Island, showing them the grooves for the first time, the first of probably dozens of times. They're going to get so sick of it. But when I teach classes on what glaciers do to landscapes, that's this geomorphology concept, that's what glaciers do to landscapes, this is just textbook place. So I like to bring students here, including young ones. With 2 slides ago, when I showed the animation of those glaciers covering the northern hemisphere, you know, planet Earth is what we call a closed system when it comes to water. We have water on our planet. Water doesn't leave our planet, and we don't gain water from outer space. Whatever water we got on Earth is the water we got on Earth. That water, if it's not in the ocean, it can be locked up on ice sheets. So when we evaporate that water out of the ocean and snow on a landscape, on a continent, and build up an ice sheet, that means the bathtub that is our global ocean has to lower a little bit, because that water's not making it back to the ocean. It's getting stored on land as ice. When that happens, global sea levels drop. Does everyone see Fat Florida? And does anyone see the ocean between Alaska and Russia? Nope, that's called the Bering Land Bridge. What about the UK and France? You could walk right between, you wouldn't have to go across the sea there. So this is the configuration of the continents and how they changed when the global sea level was lower during the Ice Age, because all that water was locked up on land. So when the Ice Age ended, in that animation I showed earlier, and all those ice sheets got smaller and smaller and smaller, up came the sea levels. So you can see here why someone who's concerned about or studies climate change today can look to the past to find all sorts of examples of in the past when sea level rose, when glaciers melted. So we have sort of a natural laboratory in the geologic history of our planet if we want to study these problems. Okay, why else is Alaska interesting? First, because it had ice sheets there. So here's the non-animated version of the Laurentide ice sheet there. You can see the title. And over on the west coast, we have a smaller ice sheet. People call it a different ice sheet, even though the two merged. And they call it the Cordilleran ice sheet because that's like the mountain west called the Cordillera. That's a word for it. What this map is showing is the movement of ancient peoples and how North America was colonized by people that migrated here across the Bering Land Bridge in the upper left from Asia. So out of Africa, people went across Europe, and they spread around the world, and people entered North America, the so-called New World, sometime in the past. And depending on what year you took your archaeology class, that number is always evolving and changing about when that happened in the past. And I'm going to tell you about when it's really different today than even when I was in school. So when were migration routes from Northeast Asia to the Americas viable for human travel? We now, in White Sands, New Mexico, have footprints there that have the record for the oldest in the past, but I'm not going to tell you the answer yet, unless you know. Okay, so in Southeast Alaska, where it says Cordilleran ice sheet, you might see those red arrows. That's what's called the coastal migration route, a hypothesis for how people came down the coast. What I wanted to do was figure out when that route became open. Was it covered by the ice the whole time during the Ice Age, or was it, when did it open for people to migrate through? Because that helps out the archaeologists in understanding the evolution of humans in North America. So that was one thing I was interested in. Here's something else. Here's two maps that have a bunch of black lines on them, bullseye shapes. Anyone know the capital of Alaska, state capital? Juneau. Okay, so Juneau is in these maps, and because the laser pointer ain't great, I'm not tall enough. Juneau is right up in there, in this map, about in the middle, and to the west of Juneau is Glacier Bay. Had big glaciers in it a couple hundred years ago, and they've been retreating a lot over the last century. And the retreating of those glaciers has led to the Earth's crust to respond to less mass pushing it down, and the Earth's crust is rebounding. Has anyone ever heard of isostatic rebound? Something that you may have learned in a earth sciences course back in 8th grade. That's when they teach it these days. I'm going to tell you later more about this rebound concept. But when glaciers are melting away, the mass that's sitting atop the Earth's surface decreases, and the Earth's surface actually uplifts due to the loss of weight that was pushing it down. These maps are showing you, these are like contour lines, like a topographic, like contour map. These are contour lines with numbers that tell you how much uplift has occurred. And Juneau, Alaska, where Juneau is, the state capital, there's a number 3 there. That's 3 meters in 100 years, which is 10 feet. Juneau is popping out of the ocean. We're worried about, most of the world, we're worried about sea level rise. Not here, because there's a local effect. Juneau has popped 10 feet out of the ocean in the last century. Think about like the waterfront infrastructure and the cruise ship docks and all the harbors. You know, another century, that's going to be another 10 feet. That's kind of something you need to think about and engineer for. So that's really interesting. Another impact of melting glaciers is a lot of flood water that's coming out from the glacier melt. And Juneau is situated down valley from a big ice field. And that ice field periodically has, it's melting kind of constantly, but now and again there are spikes in its melt when an outburst flood might happen because of the glacier geometry up valley. So Juneau in the last decade or so has been really impacted by glacier meltwater like pulses because the glaciers are retreating so fast there. And then on the right, that's the picture of Juneau and parts of Juneau, and you can see all these boat harbors and everything. So just think, 10 feet per century, this whole infrastructure is popping out of the ocean because of the glacier loss. Something that we need to plan for. Okay, so I want to tell you a little bit more about the kind of research that I do. Like in particular, I mentioned that I want to talk about my research program, and I want to tell you about my research through the lens of graduate students. I take undergraduate students to the field in field-based courses, and then at research universities, the way it works, like I got my undergraduate degree, then I got a master's degree, then I got a PhD degree so I could become a professor and teach and give back to the younger generation what I received when I was younger. So I'm helping students like Caleb and Tessa who decided, for example, they both graduated with 4-year college degrees. Tessa went and worked for a year in environmental consulting and decided that in order to really do what she wanted to do in life, she wanted a master's degree. So she comes to research university and decides to do a thesis-based master's, which is working on a piece of research that turns into her graduate thesis. Caleb's the same. He joined me from Middlebury College. He decided that he actually he had lofty goals. He wanted to become a professor and teach students and get into research and do all these things. So he started with a master's degree in my research program at the University of Buffalo. So I want to tell you about their research projects. I showed you this already, and now we're looking at this circle. This circle is where the gates, the ice sheet, could be like a door. And is that door open or closed in letting humans travel through that area? The thinking is that, sure, humans then, let's just say 15,000 years ago for now, kind of during the Ice Age or tail end of the Ice Age, the classic sort of like Clovis people that were in North America, the time that archaeologists thought a lot of times for the first colonizers was 13,000 years ago, and it got pushed back to 15,000 years ago, then 16,000 years ago. Now we have genetics, so we can find a bone of an ancestral North or South American and do genetics on it to figure out maybe what genetics tell us about their migration timing and route. So there's all this new data coming out. So we want to know, well, was the coastal route open or not? They probably had boats, but archaeologists don't think they go shoop all the way across the ocean. They think they like island hop or stay near the coast where they can hunt and fish and maintain a town and society. So here are 4 maps that zoom in on that panhandle of Alaska. And these 4 maps are 4 different reconstructions of how extensive the glacier was. Like, did it flow all the way off the land and end in the ocean? Or did it stop before the ocean and leave some islands unglaciated? The unglaciated areas we call glacial refugia. So these are the 4 maps that existed around when we were starting our work there. And we wanted to know, was there actually any evidence for places that never got covered by ice? Okay, and I felt like I could address that question. These maps have a lot of question marks. They're 4 different maps. They're you see some similarities, you maybe see some differences, but they all show a little bit of like green at the edge of the white ice that were maybe small little pieces of unglaciated area where like plants and animals could survive the ice age. So then when the glacier goes away, those are like seeds to recolonize Southeast Alaska. We call these glacial refugia. So, okay. But there's question marks. It wasn't based on very solid evidence. Was anyone here an airline pilot? Or an airline stewardess? Well, you know, if you spend a lot of time in the atmosphere, you're worried about radiation levels because there's all this stuff bombarding Earth from outer space, cosmic radiation, cosmic from the cosmos, radiation, all these small particles that are bombarding planet Earth. Has anyone ever heard of carbon dating or radiocarbon dating? Well, how does radiocarbon get created? A nitrogen-14 gets slammed by a piece of radiation, a particle zinging in from outer space, strips a proton, and that nitrogen-14 becomes a carbon-14. That's the beginning of radiocarbon dating. That's how radiocarbon dating works. Then we breathe in that carbon. We get carbon in our bodies, in plants and animals. And then once we remove it from the atmosphere, because the carbon-14 isotope is radioactive, it's a radioisotope, it decays away, and that's the clock for carbon dating. So this slide shows this process. This is radiation coming in from outer space. It bombards Earth all the time. It has in the past. It does today, right now. If you had a very sensitive Geiger counter here, you would hear it go tick, tick. And it's probably not from the paint or it's coming from the atmosphere. Very slow. Nothing harmful. But it does interact with not only nitrogen in the atmosphere, but some of these particles, like this diagram is showing, go all the way to the Earth's surface, and they create unique, brand new flavor of isotopes that otherwise wouldn't exist in the Earth's crust. So 2 days ago, wait, what day is today? Tuesday? Yeah, Sunday, I was at my kid's soccer game, and it was super sunny. I didn't put on sunscreen. I was sitting out in the sun for 2 hours. Didn't wear a hat because we were going to the Philharmonic later, and I didn't want to go in there with like my ball cap on. So I'm out there in the sun, and I got blasted. Just like the Earth's crust is getting blasted. So the Earth's crust is building up a sunburn from the cosmic radiation, just like my face got sunburned from the sun. So beryllium-10 is one of the isotopes that I work with in my lab, and it accumulates and builds in the Earth's crust the longer it's been sitting out exposed to cosmic radiation, like my face to the sun. So a glacier comes along. So glaciers shield rocks from cosmic radiation. So there's a glacier, my really fancy cartoon of a glacier covering the Earth's crust, which is gray. If a glacier blankets the Earth's surface, that cosmic radiation doesn't get through. The glacier blocks it. Well, when the glacier, so out in front of the glacier, maybe a little piece that's not covered by the glacier, that's where it's starting to build up the suntan of these cosmogenic isotopes. And then when the glacier retreats, like this, like that, then all of a sudden it starts to build up that isotope dosing or builds up that suntan. If we then go in a helicopter or a plane or by foot to a landscape like that where there was a glacier and now there's not, and we take a rock sample. We can take it back to my lab in Buffalo, and we can extract these isotopes and measure them on an accelerator, particle accelerator. And we can figure out, we can quantify the sunburn. We can quantify the duration of time that the glacier went away, and then that's been building up a new dose of isotopes. That's what we do in my lab. So let's go back to the glacial refugia. Here we are now in the field. This is one of the sites that was mapped as never being covered by ice. Well, we go there in a helicopter, and the first thing we see is a glacial erratic boulder. So for starters, we're like, okay, well, this particular dot on the map wasn't an ice-free thing. It had a glacier there. Then what we wanted to do was use our isotope method to figure out when the glacier went away, or if the glacier didn't cover that site, it would be really sunburned, and we'd be able to detect that in the isotopes we measure. So here's Caleb. And before actually he even started his degree program, I flew him to Alaska, and we met, and I showed him how to collect these rock samples. He jumped right in, collecting these rock samples with a little angle grinder and a hammer and a chisel. And he didn't know it in the field. This is a note I added after the fact, but after a year's worth of lab work in working with these rock samples in my lab and then sending them to a particle accelerator, we're able to determine when ice was there to the nearest century-ish based on this isotope method. So Caleb determined that this particular site ice was there and left 16,300 years ago. We applied this method to all these red dots in this part of southeast Alaska to build a regional picture of when the glaciers left and how they retreated back to Canada. That's what happened in this part of the world. So returning to these maps, these all show glacial refugia. These are all the places my research team went. None of them showed actually that they were glacial refugia. We've yet to this day found no evidence that there was any piece of southeast Alaska that remained ice-free. Always had glaciers over every single piece of land or island. So with a new reconstruction, we don't really know. Where was the ice edge then? I don't know. Somewhere over there. Somewhere in the ocean, maybe. We need a grant from NOAA or somebody who has access to a ship so we can go out and take new fancy bathymetry data, swath bathymetry it's called, do really good imaging of the seafloor. And that might show us where there's a moraine or a glacial boulder, and we can do better mapping out there. Remember what I said earlier about global sea level when you put all the ice on the land? Well, in this part of the world, when all the ice was on the land, global sea level was 300 feet lower. So there are actually some parts of the continental shelf that are now flooded by the ocean that may have been dry and viable for humans to live. So even though there's no places on land on today's above sea level in southeast Alaska that weren't impacted by the ice sheet, it could be that there were places offshore that were above sea level where there were humans. So that's the frontier of this research, is going offshore, trying to figure out if we can find archaeological sites or evidence about where there may have been glacial refugia that are now submerged by the ocean. So that was Caleb's work, and he got his master's degree based on that research. If you end up coming to Greenland talk later today, you'll see more. You'll see what Caleb did next. But I want to switch gears and talk about Tessa, a master's student. So Caleb learned that the ice sheet was larger than previously thought. I want to tell you about Tessa's project. I want to first tell you about Tessa's result. So this is a map from Tessa's master's thesis. It's a piece of southeast Alaska called Baranof Island. It's where this marvelous town called Sitka is. And what Tessa figured out, I'm going to tell you what this map shows and how we got it. Tessa figured out that at the tail end of the last ice age, so after the ice sheet went back, retreated back to Canada through the Inside Passage, Tessa figured out that Baranof Island, which is this island here, had a small ice cap on it. So it has some very small glaciers today, In the middle of this image up here, above the words Baranof Island, you can see some white specks, some white shapes. That's the modern-day glaciers on Baranof Island. But this blue outlined area is a depiction of maybe what Baranof Island looked like at the tail end of the Ice Age. So for people who are interested in understanding how the world transitioned from ice sheets to no ice sheets, it turns out that transition wasn't linear, it wasn't smooth, it was kind of rocky. We like got really warm, and then we got a little cold, and we got warm, and we got cold, and then we finally settled in warm. So for people who are interested in understanding that sort of turbulent times of getting shaken out of the Ice Age into today's world, these kinds of maps of where the glaciers were during certain time periods are relevant for those people studying that thing. It's a small little add-on to our knowledge of the history of Southeast Alaska. I want to tell you what were the methods that we used to think that there might have been an ice cap covering Baranof Island that maybe looked like this. And these methods involve lakes and all the mud that accumulates at the bottom of a lake basin. So you go out here to go fishing or in your boat, or chuck your anchor in the water, and you pull it up and it's got moss and all over it, and sometimes it's got a bunch of mud in it. So lakes accumulate mud layer by layer below the water. And all those layers have information for us. This is a lake called Baranof Lake. It's in the middle of Baranof Island. We flew in here in a float plane and stayed in a Forest Service cabin at the edge of this lake, and we stayed there a week. And out of the plane, we threw onto the beach our inflatable boats and a bunch of what we call coring equipment, because what we do is we take core tubes and we stuff them in the bottom of the lake, and we want to bring up core samples. So this river is draining the modern-day glaciers that live in the mountains under the airplane. So glaciers are in those mountains. The glaciers melt into a river. That river flows into the lake, and that river brings in glacial sediments. Some people call it rock flour, and they bring it into that lake. So here's the boat picking us up in Sitka, and there's all of our camp for a week, and all of our scientific equipment, and our collapsed boats, and our core tubes. And then we get to the lake, and we inflate our boats. You can see the one on the right, that turquoise one, is what it is. It's has anyone here ever been down the Grand Canyon in the Colorado River or done whitewater rafting? Exciting. So these cataracts are meant for whitewater rafting. So I bought one of those, and then I gave it to my machine shop people and said, take the seat out of the middle, put some floorboards around it, and make me a tripod. And we turned it into a portable sediment coring platform. And then we got a little boat that helps us move around. So, this is a video. Let's see if I can get this to work. Okay. So that's Tessa on the right and Michaela, another student on the left. These two lines that they're pulling are pulling up a hammer, and then they're dropping it. Pulling it up, dropping it. Pulling it up, dropping it. And that hammer, going up and down, is hitting the top of a core tube. 3-inch scheduled 40 PVC pipe from Home Depot. And that's getting pounded vertically into the bottom of the lake. Then we pull it up, and we ship it back to Buffalo, and we study it. We did a test core that before we knew we were playing for keeps, we kept it in the core tube and shipped it to Buffalo. We did a test core, which we usually do, and we extruded it on the deck, and then with a pocket knife, we cut the core sample down the middle, and it fell open like a filleted fish, kind of. And that's what we're looking at there. So this is our Tessa being happy about her. When you go do these things, you're like, oh my God, am I going to get any samples so I can do a master's thesis? What's this Briner guy doing with me out here? What if we don't get any samples to bring home? So when we got the mud in the tube and we proved that we could go get it, she's relieved. She's like, okay, I have a master's thesis in front of me. So she's particularly happy there. Here's what some of the sediments look like. So this is just a still picture of a core. That's a sediment core. Like I said, we fill a Home Depot 3-inch PVC pipe with mud, and then we flail we bring it back to the lab and we cut it lengthwise on both sides, and then let it fall open. And then we can look at all the layers that have accumulated in the bottom of the lake. And then this is a scientific diagram of core photographs and a little cartoon of what the sediment looks like. This is classic geology, where we do stratigraphy. You do the same stratigraphic analysis in the layers of the Grand Canyon and any like rock formations. So this is classic like geological stratigraphy, we call it. And then those numbers are our radiocarbon dates, our carbon dates, so we can get timeline. And we basically determined from this sediment from the lake that when the glacier is big up in the top of the valley, this lake has a lot of glacial silt coming into it. And when the glacier is small at the top of the valley, the mud in the bottom of the lake is just really organic rich, not silty, very like just high in organics, like wood pieces and leaf pieces. And then when it's a glacial environment, it's not like that at all. It's highly layered, very silty, and we interpret those sediments to indicate what the environment was like. So that's how we were, combine that with carbon dating, that's how we were able to make some inferences about what the glaciers were like in this area. So Tessa's master's thesis was just published in, I think March maybe, March or April. She got a research paper out of her master's thesis. This is her article. And she's now back working as an environmental consultant in the Philadelphia area, a company called Ramball, where she's like a practicing geologist with a master's now. What we did also with that work, when we were, you guys know what fish finders are? So this is like an instrument that's on your boat and it tells you how deep the water is. Well, part of our scientific equipment, we have a fancy fish finder, and we make bathymetric charts of all the sites we go to because that helps us figure out where to strategically take our core sample. No one in Southeast Alaska and the neighboring communities had ever had a detailed bathymetric chart of this lake, but a lot of people fly here and float planes and fish. People boat around to Warm Springs Bay up there where there's a hot spring and they hike up there, and there's canoes and people paddle around. So we made this bathymetric map of Baranof Lake and we gave it to the community. So now the Forest Service has it and the community has it for whatever use they have. So this is the first bathymetric map that we made and we gave it to the communities. I want to get into the final chapter of this talk. And I want to come back to sea level change. We've talked about a couple of different methods of how we reconstruct glaciers and how they've changed in the past. I want to talk a little bit about sea level now, how we know sea level history. And to do this, I want to introduce a current master's student of mine named Jerry Stoller. Here's Jerry. She's from Colgate University, undergraduate degree from Colgate, and she joined my group because she wanted to do a master's degree in some kind of like glacier sea level research project. So we brought Jerry to Alaska last summer. We got to the Coast Guard up there. So the Pacific Ocean is a huge thing, and there's a lot of people in Alaska that go off in the Pacific Ocean and fish all the time, right? Or sightsee or whatever, and people need help. So there are two huge Coast Guard stations operating in the Pacific Theater. One's in Kodiak, Alaska, and one's in Sitka, Alaska. And the Coast Guard is like, to me, what I've learned. I have a brother who's a career firefighter, and the Coast Guard reminds me a lot of like, I call them like firefighters of the sky. They're just like the friendliest, most outgoing people you'll ever meet. And they get it approved through their district command, help. They partner with the Forest Service. We partner with the Forest Service, and they're able to help us out with some logistics. So some of the study sites we want to get to, we charter commercial planes and commercial helicopters. Now and again, when we're lucky, we get the Coast Guard to help us out. So the Coast Guard, in a partnership with the Forest Service and our university, helped us get out to some research sites. Okay, I want to revisit these maps. This is what's happening today. The left one is the uplift rate. And those bullseyes tell you that that's where the crust is uplifting the most. The right is telling you it's a little piece of that map that tells you how much uplift there's been in the last 100 years. 10 feet at Juneau. Look at those 6. See up in Glacier Bay National Park, there's all sorts of cruise ships that go up there to look at the glaciers. That number 6 up there, that's 6 meters. So that's like, that area in 100 years is popped out of the ocean 20 feet. That's just incredible, incredibly fast. Okay, here's my little thing on isostatic rebound. You see the bear sitting on the trampoline? See the trampoline bottom below the weight of the bear? That, believe it or not, that happens to the Earth's crust. It actually does. So the crust sinks below the ice, and there's all this weird stuff, like the edges might bulge, like if you lay down in a waterbed, the edge might bulge up a little bit. That happens to the crust too, all this weird stuff. And then let's say the glacier goes away faster than the crust can respond, and then we're left with a depressed piece of crust, and then the ice goes away, the sea level floods the Earth's crust because it got pushed down by the weight of the glacier, then eventually the crust readjusts back to normal. So that's interesting. There's a lot of parts of the world now where the crust is still adjusting from the last ice age. So if we want to predict sea level rise in New Orleans, New York City, Oslo, Norway, we need to understand the memory that the Earth's surface has from the Ice Age. Because that's impacting, it's changing the global rate of sea level change locally, because there's this nuance of this memory of the Earth's past. We need to understand that in order to predict more precisely sea level change today. There's cool things like this. This is it's kind of a bad picture that I took of right by a river, like a stream bank. If you were like to look at a river, it erodes into the bank and carves off a little bit of the sediments or the rocks. This is a stream bank picture I took, and see the clamshells in there? Loaded with clamshells. But this is like 15 feet above present day sea level, above the tidal zone. This is a part of the Earth's crust that was below the sea that's popping out. And we can carbon date those shells to figure out the history of that sea level change. I want to close by telling you about Sitka, Alaska. It's a place that if they had a job for me, I would move yesterday. I'm in love with this town. We've been doing research here for a number of years. Last summer, my wife and I brought our boys up there, and we lived there for a month, and they were just out fishing and hiking and just loving it. It's a wonderful town. Highly recommend you visit. It's on the outer coast of Southeast Alaska. Cruise ships go there. There's this beautiful volcano called Mount Edgecombe. This thing erupted, blasted, like Mount St. Helens did in 1980. This thing blasted like that, but only 13,000 years ago. And it put an ash layer on the town of Sitka that's like my height thick. So the town of Sitka is built on this ash layer. So people are a little aware of this sleeping giant next to them and hoping it doesn't do that again. Aerial view of Sitka. So there's the runway that Alaska Airlines flies to, so you can fly there also. And I want to point out this lake in the middle of the town called Swan Lake. It's like the town park in the middle of town. See how it's kind of like, almost looks like a fish or something. I don't know what that looks like. Anyway, that's a lake. It's called Swan Lake. Swan Lake is sitting at about 27 feet above sea level. Swan Lake, we think, used to be pushed down in the ocean. And today it's a lake because as the crust adjusted from the Ice Age, what used to be a marine basin is now a freshwater lake. This is a map that I made using new LiDAR data of the town of Sitka, and I drew on top of it that blue line, which is my guess of where the sea level was when the glaciers went away. The crust was pushed down. But today the sea level is, you can see below the blue at the bottom there are these harbors and the coastline and stuff like that. If only there was a method we could do to figure out if that's true or not. How could we go to Swan Lake today and figure out if it used to be marine, part of the ocean? Well, we had some leftover core tubes. So we got our coring rig on the town park lake, and we pushed our Home Depot white pipes down to the bottom. There's Jerry with my colleague Jim, who's a Southeast Alaskan, and a postdoc named Sam who was with us. And you can see there's mud slathered on the outside of that core tube because that's when we got done coring. We filled that whole thing with mud, brought it up. And what we did was we opened it right in front of the town, the community. We advertised to the community that we're going to be out here on your lake today. We're going to take a core, we're going to bring it up, and we're going to split it open so you could all see. So it was a rainy day, of course, because it's always raining there. But we had a little tent covering this, and you can see the cores that we opened up. And you see the white things in the bottom? Those are clamshells. Sure enough, even though it's a lake today, we got through the freshwater sediment layers, and we got down into the different kind of mud that has filled with clamshells. So we know Swan Lake was part of the sea, and we carbon dated what Jerry did. Jerry carbon dated organic fossils in the mud layers to figure out when it popped out. That's what she's doing for her master's thesis. This is a scientific poster that Jerry presented at a conference that we held in Buffalo in March. People from all over the world came to Buffalo for this thing that we call the Arctic Workshop. Happens, well, now it's every other year. And we were lucky to host it this year. And this is the poster that Jerry made for that workshop. And so she's got one more year of her master's thesis, and she'll write it up. So that's it for me for this talk. I just want to acknowledge how we're funded to do this research. So, I work at the University of Buffalo. I call my lab the Glacier History Lab. And, I get paid during the academic year to teach classes and advise students and help the university on its mission. And then in the summer, I don't get paid by the state, by New York State, but I need to raise my own funds so I can do research like this, to work on societally relevant problems, and also to train students so they can work on their graduate work. And the research in Southeast Alaska is funded by the National Science Foundation. And there was 1 or 2 years when I got some generous support from the National Geographic Society. And that's it. I'll say thank you, and then Gunal Shish is thank you in Tlingit.
Thank you, Jason. Does anybody have questions?
I think there's a microphone involved, so Sarah will do that part.
Has the funding for the NSF changed recently?
That's a very depressing topic for me. The NSF is a $9 billion year funding line from Congress. And for like the past 5 years, that number has been pretty fixed, has not kept up with inflation. The rest of the world is going like this. NSF's allocation from Congress has been flat. And 1 year ago, the president wanted to slash it from $9 billion to 3.7 or 3.9 billion. Congress did not approve that. They funded it at 8.7 billion. Those funds that Congress said that NSF should get eventually landed at the foundation in February, but then the NSF needs to create a spending plan to figure out how to distribute those funds to all the proposals that they've been in the meanwhile getting. Sorry, this is a long answer. It's on my mind a lot. It's a good question. So today, they're developing their spending plans, and they're trying to distribute grants to university researchers so they can keep their active research programs going. In the meanwhile, though, the board, there's an independent board of 15 scientists and folks from industry and academia and whatever that oversee and help NSF in its decision making. They were all released. And there's a concern that a lot of the funds, even though Congress put funds to NSF, that they're going to get used in ways that aren't necessarily going into academic kind of research. It might get pivoted into other areas. So At the University of Buffalo, I recently switched roles a little bit. As of this summer, I'm entering the Dean's Office of the College of Arts and Sciences as Associate Dean for Research, in a very tough time for the research mission of universities. So I've been thinking about this topic a lot in addition to my own research, but just sort of how we're going to get along as a research university. Sorry, long answer.
Going way, way back in time, the Earth has had at least one, perhaps more, snowball Earth episodes where the entire Earth was covered with glaciers. It managed to come out of those because volcanoes were not stopped, and they belched a lot of carbon dioxide. Carbon dioxide helped warm up the Earth, and we eventually got back to this. How much carbon dioxide is expelled by volcanoes versus our usage of carbon-based fuels?
That's a very nicely articulated question. Thanks for that. Those episodes in Deep in Earth history called Snowball Earth, fascinating times, billion years ago, 500 million years ago, when people do think the Earth was covered in ice. And that's true that there were long-term, widespread episodes of volcanism that maybe shook us out of that and got us away from those ice age conditions. So you asked so there are volcanoes erupting every day on Earth right now. Most of them small, some large. The carbon dioxide that's coming out of those volcanoes is extremely small compared to the industrial release of CO2 in our atmosphere. I don't have a number for you. We could look it up. It's readily available information. I think part of the issue is time scale. So shaking Earth out of a snowball Earth phase is probably a geologically long process. Not a year, not a decade, not a century, maybe 1 million years, or at least hundreds of thousands of years. And these are time periods when the rigor of plate tectonics was moving fast. And so these were time periods in geology where there was just a high frequency of volcanism over a prolonged period of time because the rates of subduction zones and plate tectonics was fast enough to get us in more of a volcanic phase to shake us out of those snowball things. Today, the human activities related greenhouse gases, including carbon, but other ones too, methane and stuff, that's happening fast. We're at a decadal century kind of uptick there. And the volcanoes that are popping off every day are kind of small things. Now and again, there is a bigger volcanic eruption that would release, that's more like what we call effusive rather than explosive. The Mount St. Helens aren't the ones that are giving a lot of CO2 out. It's more like the Hawaiian style. But that on a grander scale would be the kind of CO2 that we would need to compete with the human-caused CO2. But in the last century or so, the volcanic source of CO2 has been minuscule. I'd probably say like less than 5% of what the human-dominated CO2 release is.
Early in your talk, you talked about water being a closed system on Earth.
Mm-hmm.
I've read, and I don't know if it's proven or if it's theoretical, that all the water on Earth came from meteorites. Didn't originate here. Somehow it was, out in the solar system and landed here. Is that really the accepted explanation for how water got on Earth?
That is not something I know very much about. I don't know the answer to that. Yeah, it could be comets and all this stuff slamming into Earth in those hectic early days.
Any other questions?
I was in Glacial Bay a couple years ago and saw glacier calving, and I was just wondering if that's happening more frequently now, or it's a steady amount that's always happened?
Yeah, that's a good question. Glacier calving You know, the creation of icebergs. These are glaciers that flow into the ocean, and then they might like float a little bit, and then they break off and calve. That's a calving event, making an iceberg. Totally natural process, happening all the time. Any glacier that flows into a lake, into an ocean, is gonna be, you know, glaciers are flowing constantly. They look solid and like they're just frozen and not moving, but if you've ever seen like a time-lapse movie of a glacier flow, they're like flowing all the time. So they're always flowing into the sea, creating icebergs, natural process. There are some parts of the world where the calving rate is like particularly high. Some glaciers in Greenland, some glaciers in Antarctica that are undergoing sort of like they're going through like little collapse moments, then calving can really spike. Probably the glaciers you saw, like maybe they're calving a little bit faster because the glaciers overall are like retreating today, but probably my guess is not like noticeable to us like going to visit for a day boat, you know, a day trip or something. Largely a natural process.
All right. Any other questions? All right. Thank you, Jason, so much for coming and sharing today.
I'll just mention that I do have some flyers up here if anyone wants to. There's like a QR code to my website and my email if anyone wants something like that. You could always contact me later for your Ice Age questions.